So today we will derive a formula which is a very simple formula because it's just a trace of a matrix. But this formula captures all the essential features of the formulas that periodic orbit theory deploys to compute expectation values of any log-time average. If you understand this, you understand 1/3 of what's going to come. And the basic observation is the following. If I have some matrix, for example, we'll take as the simplest example the binary system where I can go from 0 to 1, from 1 to 0, and go 1, 1. The transition matrix is 1-by-1 matrix, but I will be a little bit pedantic and I will write it explicitly as matrix element 1, 1. So now consider t square. As I multiply this by itself, up here I'll get t11 square. As I multiply this, I'll get t12 times t21. Here I get 2 square plus t that starts at 2 goes to 1, goes from 1 goes to 2. I get things like t11, t12. Now let's multiply this one more time. So what happens? 3 steps forward in time. I observe that here I get t11 cube plus t12, t21, t11. And then I get So now let's look at what these terms mean. This term means that I was at 1 and I stayed at 1 twice. So let me define a little t1 to be just this matrix element. This one says that I started at 1, I went to 2. So let me define a 2 cycle to be the link going from 1 to 2, to 2 to 1. So that's a closed walk of length 2. And I'll ignore stuff off diagonal, as you'll see. Right now we don't need it. So I'll call this a little trace. It has to do something. It sits on the trace of the formula. Now when we look at the third one, if we start at 1, we go to 2, then from 2 we go to 1, and then from 1 we go back. So let me call this t1 to 1. And this is obviously the same story, just permuted cyclically, but it doesn't matter, it's a product of 3 numbers. So this will become 2 times. So let me just write these things in this little trace notation. 1 square, which means I stayed at the same spot twice. This one is t2, stayed at 2 twice. Or I start at 2 and I go to 1. In this case, we have a t1 stay there for 3 times plus t1 to 1 And now I notice the following thing. If I just look at a trace of t, t11, this guy here, plus t12, t22, if I take a trace square, this is either stay or hop between 1 and 2, but by cyclic permutation of the trace, it's the same as 1, 2, 2 times t12 plus the second one squared. And you see the very simple structure. The trace is all possible walks of length 2, of length 3, which are recurrent, which come back to the same point, so they're periodic. And this is why the periodic orbits will show up eventually when we start computing general dynamical systems, not just topological trace formulas. So the general structure of this thing is that the trace of t to the n, which happens to be also the number of all periodic orbits of length n, because we explained that what the power of transition matrix counts all possible ways from getting from I to j. And if you identify I to j counting all possible recurrent walks, meaning walks that start someplace, come back, in other words, periodic orbits, you'll have a property that will be sum of all prime orbits, meaning that this itinerary is not a repeat of a shorter one, so all prime orbits. For each prime orbit, you'll get the number of periodic points, because each periodic point contributes to the trace. In third power, what used to be periods 3 are now fixed points of the third power of evolution. You remember that from other examples. Then we'll have sum of all r goes to 1 to infinity, and for each one of them we'll have the weight of that prime orbit, for example 1 or 2 repeated some number of times, and the whole thing will have to add up to n. So r repeat times the length of a prime cycle. And this is what you see in this formula. These are two distinct cycles of length 3, so they show up only as a 1 repeat. And r equals 1. And then the 2 prime cycles of length 1 are the fixed points, and they show up as a third power. So having made this observation, you can derive a very elegant formula that will relate topological entropy in this case. That, you're just defining this little trace, and right now little trace is 0 or 1 depending whether that prime cycle exists or not, but notation will carry over in the general case where actually will give weights to cycles. We can define a generating function of cycles of all length, starting with the fixed point and going off to infinity. That will be the sum of prime cycles. The sum of their repeats goes from 1 to infinity Zn delta function, and prime cycle repeated r times. This will always give us a 1. This is just a delta function. So we will get the generating function is given by all lengths of prime cycle, all their repeats, c to the length of prime cycle times its repeat. From here, times the weight of a prime cycle. repeated r times. But this is a geometric series, so we know how to add up that thing up. So this is a sum for all prime cycles. It starts with 1, it's z. For each prime cycle we can do the sum, and it's z to the n prime cycle, its weight, and then the rest is geometric series. 1 minus z length of the prime cycle. But we also have an explicit formula for this. And the explicit formula is that this is the same as Zn trace of n goes to 1 to infinity, nth power of our transition matrix. That's also geometric series, so we can sum it up. So this is a trace of Ct divided by 1 minus Ct. This is a trace, so we know what a trace of a matrix is, sum of its eigenvalues. So this is the same thing as the sum of the eigenvalues of the matrix. Alpha goes from 0 to whatever the dimension is, z, and for each one we get lambda alpha 1 minus z lambda alpha. So here we are, as advertised, the topological trace formula. Totally simple algebra. Is this convergent? Well, lambda is some sensible matrix filled with zeros and ones, so it has some sensible eigenvalues. And as long as z is sufficiently small, there is no divergence here. And lambda is a finite matrix, so this is a finite sum. So as long as z is smaller than the leading eigenvalue of this matrix, because inverse of the leading eigenvalue, because when it's inverse of the leading eigenvalue, that'll be the first time we get a 0 on the left-hand side. So left-hand side is okay. Now, the right-hand side you can worry a little bit. But it's got to be convergent because the left-hand side is not convergent. But right-hand side is remarkable. It says that if you know all prime cycles, all, because we had to sum this whole thing to infinity. So if you do just counting of recurrent orbits, we will get a full spectrum of the transfer matrix. And the leading eigenvalue, which we showed last time, its logarithm is topological entropy, will be given by this sum. So this looks pretty brilliant, and how is it going to work? It's not at all obvious it'll work. And I'm sorry, I've forgotten there was an NP. Length of the cycle was still here. That's important. So every periodic point, not just every periodic orbit, but every periodic point contributes to this.